In this movie, I'm going to discuss the equivalent circuit of an axon and the electronic components that comprise axons. So this is a drawing of the electronic components that comprise the axon. The outside is indicated in blue, that's the extracellular fluid, and the inside of the axon is indicated by white. And as you can see, there are 1, 2, 3, 4 different blocks there. Each of these blocks represents the building block of an axon and the electronic components that comprise those building blocks. And there are 3 that are of significance. The first one is shown here. It's labeled CM, and it stands for membrane capacitance. And what that means is the membrane is actually the equivalent of an electronic component called a capacitor. And a capacitor is something that students, or at least most students, have very little familiarity with, and this causes them to freak out to no end. It isn't that difficult. I'll explain it to you simply in just a few moments. The second component is the membrane resistance. And what that refers to is how difficult it is for current to flow through the ion channels in a membrane. And that just means how many ion channels are open. That's really what it refers to. And again, I will explain this to you in greater detail in just a few moments. And the third thing is the R internal, which stands for the internal resistance of the axon. So now what I'd like to do is explain this to you by using an illustration of an axon shown in the lower part of the figure. And here I've put in a bunch of channels. They happen to be purple potassium channels, but the kind of channel doesn't really matter at all. And here's the point. First, let's consider the capacitance. And the capacitor is nothing more than the cell membrane. What a capacitor is simply an insulator that separates 2 conductive plates. The insulator in this case, of course, is the cell membrane, and one conductive plate is the extracellular fluid, which is salty, and the other plate is the intracellular fluid, which is also salty. And they hold and separate charges across the insulation. And in this case, it's the resting potential. Negative charges on the inside relative to positive charges on the outside. That's all it means. The next component is the membrane resistance. And as I've indicated to you, that's determined simply by the number of ion channels that are open, because they determine the resistance to current flow through the membrane. So if there are no channels that are open, the current flow is almost infinite. The membrane resistance is extremely high. If we open a channel, now current can flow through that channel and the resistance is reduced. And if we open another channel, even more current can flow and the resistance is further reduced. Hence, the membrane resistance simply is an indication of how many open ion channels there are in the membrane at any one time. And the third thing is the internal resistance of the axon. And what that's going to be determined by is the size of the axon, because that's going to determine the resistance that the axoplasm presents to the flow of ions down the axon. So small axons will present a large resistance, and as the diameter of the axon becomes larger, the resistance will fall. It will present less resistance. And as we'll see, the resistance to flow down the axon is probably the principal determinant of the conduction velocity of an action potential. I would add one final point here, and that is this particular demonstration, or this illustration, is for what are called passive properties. In this particular situation, there are no voltage-sensitive channels at all. Nothing is gated or changed by voltage. Things just pass down the membrane passively. So features that are voltage insensitive are known as passive properties, and those that invoke or recruit voltage-gated channels where things change dramatically are called active processes. And what we're talking about here are simply the passive properties of an axon. So now let's consider in a little more detail how a capacitor works. And as I've indicated to you, it's nothing more than two conductive plates separated by an insulator. In this case, the insulator is air, but it could be anything, so long as it doesn't conduct electricity. And as you can see, both plates are attached by wires to a battery. Let's say the battery has a 1-volt battery, just for argument's sake. And the switch is open right now, so nothing is happening. And let's see what happens when we close the switch. So we close the switch, the circuit is completed, and all of a sudden, a humongous amount of charge accumulates on the top plate, positive charge running from the positive pole that repels the positive charges on the bottom plate, making the bottom plate negative. So this battery will transport charge from one plate to the other until the voltage produced by the charge buildup is equal to the battery voltage. So in this case, it would be 1 volt because I made the battery 1 volt. Right? And I can plot how long it takes for that charge to build up. And that's shown on the right-hand side. I'm going to plot voltage on the y-axis and time on the x-axis. And there's that little switch, and I'm going to close the switch. And as soon as I close the switch, the current builds up immediately. That is, the charge builds up immediately on the positive plate and repels the positive charge from the negative plate, and the capacitor is fully charged. And the capacitance, by definition, is equal to the charge per volt. In other words, how many charges does it take to change the voltage across the capacitor by 1.0 volts? We won't be considering 1 volt, we'll be considering millivolts, so you can think of it as how many charges does it take to change the charge across the capacitor membrane by 1 millivolt. That's an easier way for us to think about it, but you get the point. Now, the capacitance, therefore, is going to be determined by the size of the capacitor. So let me illustrate that to you. Let's take a capacitor that's larger. It's twice the size of the other one. The plates are twice as big. And now we connect it, and voila, what you get, again, an immediate buildup, but now there are twice as many positive charges on the top plate than there were on the smaller plate, because it can hold more. In other words, with a larger capacitor, it's going to take more charge to change the voltage across the capacitor. That's the point. Now, I want to illustrate this by looking at a cell, an axon, and seeing how this idea of capacitance has meaning for the depolarization of an axon. So, here we have two axons, a very large one on the left and a small one on the right. And they both have a membrane potential, a resting potential of minus 70 millivolts. And now what I'm going to do is I'm going to inject a fixed number of charges into the large axon and change the membrane potential. I'm going to inject 1, 2, 3, 4, 5, 6 charges. And those positive charges are going to be attracted to the negative charges on the inside of the membrane, and they're going to negate some of them. But of course, this is a large axon with lots of negative charges, so the small number of positive charges that I injected only negated a few of them, so I've only changed the membrane potential slightly to, say, minus 60 millivolts. All right, now here's the point. I can do exactly the same thing and inject exactly the same number of positive charges into the small axon, but the small axon has a smaller number of negative charges on the inside because it has a smaller capacity. That is, the capacitor doesn't store as many charges, it's smaller. Now watch what happens. I inject the same number of positive charges in, but I can negate so many more because they're just a fewer number to negate. And as a consequence of that, the same number of charges depolarizes the axon by a much larger amount. In this case, I made up the number 40 millivolts. But the point is, for the same number of charges, because the larger axon has a larger capacitance, that is, it takes more charges to change the membrane potential by a millivolt than a smaller axon does, because the smaller axon has a smaller capacitance. That's the major point.